Another very common application is to do sequence to sequence modeling, right? We do the language translation. So again, this is many-to-many mapping, right? So we have a input sequence, and we also need to generate output sequence, maybe in a different language. So in this kind of sequence to sequence network, usually they have an encoder and a decoder. Okay, so the encoder here is responsible to encode some of the features of the input, and the decoder is going to using this hidden state to decode, right, to translate to a different language. So typically after the encoder, the last hidden state will pretty much capture all these information, and this hidden state will be used as the initial hidden state at the decoder stage to do the translation. So in this case, there's the challenge in language translation is that this hidden state needs to memorize the whole input sentence, right? So this is going to be quite challenging, because if we have a very long sequence, it will possibly this hidden state wouldn't able to capture this long range correlation very well just for this hidden state. So this kind of inspire or motivate researchers to think about, is there any a better way to model or pay attention to a specific region, right? So that some of the correlations can be learned better. So that's why this attention mechanism is being developed. So this is the maybe the first reference or paper described this attention mechanism technique. So the idea is that it will allow a model to automatically search for parts of a source sentence that are relevant to predict a targeting word, right? So basically, you want to, instead of memorize the entire long sequence, which may not be able to achieve a very good job, then in this case, can we search for a particular part, right, of the sentence that are most relevant to predict a target word, right? Because in translation, not all the words may be necessary to predict a particular target word, right? So we don't have to memorize all of them, but we can find those important parts or salient parts so that we can just memorize those, and hopefully this will give a very good prediction. Okay, so in their paper, they actually did a comparison with between the recurrent neural network without attention mechanism and also their proposed recurrent neural network with attention mechanism, right? The search for the parts of the sentence most relevant to the target word to be predicted. And this is a figure showing their performance. They're using this BLEU score. So this is a metric used for evaluating the performance of translation. So the higher, the better. So from this figure, right, they using the traditional encoder decoder based RNN architecture to do the translation. And when the sequence lengths become longer, right? So here, the horizontal here is the sequence length. When it become longer, the performance goes down dramatically, right? You can see the BLEU score going down very quickly. But if they're using their proposed technique, right, to search for the parts that's are most relevant to the word to be predicted, they are able to maintain a very high BLEU score, even when the sequence length is going to increase a lot, right? From maybe 10, 20 here going to 60, they are still able to maintain a high BLEU score. So kind of demonstrate the effectiveness of the attention mechanism in this particular task, which is language translation. Okay. So next, let's look at this attention mechanism. So what is this attention mechanism is doing, right? So this attention mechanism is a technique used to selectively focus on the most relevant parts of an input, rather just using the entire input equally when producing a prediction. Okay, so before we are using language translation as an example, but this attention mechanism is not only restrict to the language translation task. This can also be applied to image classification, video classification, image captioning, or video captioning, right? So because in the image, we also need to focus on maybe particular region, right? When we generate the caption or make a classification, maybe some of the parts are more important than the others, right? We call this salient region, so that the prediction can be more accurate. So this attention mechanism allows a network to dynamically weigh the importance of different elements in the input and focus on the most relevant ones when making a decision, right? Basically, we want to weigh these different elements and only focus on those are important for the decision making. And this attention mechanism has been proved particularly useful in many applications like machine translation, image captioning, when a model has to consider different parts of input when making a prediction. Okay, so this is very intuitive, right? It's just like a human perception, or when the human perform a certain task, right? We always focus on the important parts, rather, kind of divert our attention to all the components, which some of them may not be useful. Okay, so let's again using translation as an example to see how the recurrent neural network can be combined with this attention mechanism. So let's look at this. That's using bidirectional RNN. So because this is more advanced in machine translation. So basically, we just consider like two paths, right? So we had a forward path, HF, F indicating forward, and we also have another path which is backward in the opposite direction. So the x0, x1 to xt minus 1 is the input. So you can consider these are maybe some sort of feature embedding of a particular word. Okay. So in this case, we can generate in the forward path, we have a hidden state, hidden embedding H, and the backwards, we also have a HB here. So then we can simply, combine them or concatenate them together, right, to form this embedding H1. Okay, so here we can do this for the other input. We have this hidden state H1, H2 to HT minus 1. Okay. And then we can, based on these hidden state, and we generate the attention weights, right? So how much we have to weigh these representations or embeddings, right? So we have alpha 1, alpha 1, 2, and alpha 1 t minus 1. Okay, so here is the equation, right? So we have all these, t different hidden states. Then we want it using a coefficient or weights alpha here to weigh them, right? Maybe some of the hidden state are more important. Maybe some of the hidden state are less important, right? For predicting this particular output here, y1 hat here. Okay, so this is a weighted sum, and we resulting a context vector C1. Okay, so if we just look at this particular example here, so we have a C1, right? Because H is a embedding, right? So it's a vector. Alpha here is the weighting value, right? So we do this weighted sum and we generate a context vector. So because the reason called a context vector is you look at all these different input, right? So you have some understanding of the entire sequence and understand the context, so that when you make a prediction, you take these contexts into consideration so you can make an accurate prediction for the translation. Okay. So you may wondering, right? So understand this weighting strategy, right? To weigh these different embeddings, but how do we generate these weights, right? This attention weights. So this also can be made simple, right? So here, what we can do is we can using a neural network to learn or to generate this attention weights, right? So this we can using a simple multi-layer perceptron, right? Take the previous hidden state in the decoder and these from the previous step and the hidden state together, right? So to generate these attention weight. So here, because we are using the neural network, maybe this value is not normalized, so it can be any value. So to kind of have a nice interpretation, right? So as a weighting, right, we can using just like we talk about the fully connected layer to do the classification, right? We can using softmax to normalize them these values between 0 and 1, right? So and these all sum to 1. Okay, so we can again using the softmax to do that. And so this is how we can generate this attention weights, and once we have that, we can even plot these weights and to have a nice visualization, right? So for this kind of a translation, right, this sentence, I think maybe from English to I'm not sure, maybe French or other type of language, right? So what is the tension, right? So between this one particular words and the weights for the other words in this sentence. Okay, so we can using this plot this weight as a visualization. So again, so this is just the figure took for their paper with the attention mechanism with their RNN, so they are able to improve the performance when the sentence is long. Okay.